Deep Dive, Sable Offshore. Part 2, the 11-year shutdown, corrosion, integrity, and the physics of dormancy. The shutdown of the SYU in May 2015 was not a planned decommissioning, it was an emergency stop following a failure. In industrial systems, an 11-year shutdown is not preservation, it is entropy. Over that span, mechanical integrity degrades, safety systems lose reliability, and restart feasibility becomes uncertain. While steel structures do experience an initial period of stress relaxation after installation, long-term dormancy does not produce a stable equilibrium. In pressurized pipeline systems, safety depends on active control, flow, temperature, pressure cycling, corrosion inhibition, and continuous monitoring. When a line is shut in for years, protective conditions decay. Residual moisture and contaminants settle into low points. Oxygen ingress becomes uneven. Cathodic protection systems lose effectiveness. Seals and coatings age, and localized corrosion mechanisms accelerate rather than stabilize. In practice, extended inactivity increases uncertainty around wall thickness, defect growth, and material toughness, meaning that an 11-year shutdown leaves a pipeline less predictable, not more settled, than one kept in controlled operation. The 2015 Refugio spill, origin of the crisis, on May 19, 2015, line 901, now line 324, ruptured, releasing roughly 140,000 gallons of crude oil. Approximately 21,000 gallons reached the Pacific Ocean via a culvert under Highway 100 and fouling beaches and killing wildlife. The failure was traced to external corrosion that reduced the pipe wall to a fraction of its design thickness. The regulatory response was swift and severe. The operator at the time, Plains All-American Pipeline, faced criminal charges and entered a federal consent decree. The assets later passed to ExxonMobil, which ultimately sold them to Sable Offshore in 2024 after failing to restart the system under California's regulatory regime. The failure mechanism identified in 2015 remains the central technical issue today. The Refugio spill released approximately 140,000 gallons of crude oil, of which about 21,000 gallons reached the Pacific Ocean, making it one of the most significant coastal oil spills in California history. The incident resulted in the deaths of roughly 350 birds, impacted marine mammals, forced the closure of multiple beaches, and disrupted fishing and tourism along the Santa Barbara coast. Cleanup, remediation, and legal settlements ultimately cost around $63 million. While small in scale compared to major disasters like Exxon Valdez, about 10.8 million gallons, or Deepwater Horizon, about 134 million gallons, Refugio's location in a highly visible, environmentally sensitive, and politically active region gave it a disproportionately large social and regulatory impact, hardening public opposition to offshore oil and reshaping California's regulatory stance for the next decade. Corrosion mechanisms, CUI and MIC. The prolonged shutdown amplified two distinct corrosion risks. 1. Corrosion under insulation, CUI. Corrosion under insulation, CUI, occurs when the insulation wrapped around a pipeline used to keep heavy crude warm enough to flow begins to fail and allows water to penetrate. Once moisture becomes trapped between the insulation and a warm steel pipe, it creates a high-humidity microenvironment that aggressively accelerates corrosion. The image illustrates this failure mode clearly. Water seeps beneath the insulation, rust spreads along the pipe surface, and corrosion progresses unseen. Critically, the insulation also creates a shielding effect, acting as a dielectric barrier that prevents cathodic protection current from reaching the steel. When this happens, corrosion is no longer actively mitigated and can advance unchecked. This exact mechanism, hidden corrosion beneath intact-looking insulation, was identified as the direct cause of the 2015 rupture and remains the primary technical concern of regulators today. 2. Microbiologically influenced corrosion, MIC. Microbiologically influenced corrosion becomes a serious risk when pipeline flow stops and entrained water settles along the bottom of the line. In stagnant conditions, sulfate-reducing bacteria can proliferate within this trapped water, forming biofilms on the steel surface and producing hydrogen sulfide as a byproduct. These biofilms create highly localized electrochemical corrosion cells that aggressively pit the pipe wall from the inside. Under normal operation, continuous flow suppresses MIC by sweeping away water and microbial colonies, but during prolonged dormancy the process accelerates unchecked, thinning the steel internally and often remaining undetected until a leak or rupture occurs. This image illustrates microbiologically influenced corrosion, MIC, a process where stagnant conditions allow sulfate-reducing bacteria to settle at the bottom of a pipe and form protective biofilms. These bacteria produce hydrogen sulfide, H2S, as a byproduct, which creates highly localized and aggressive pitting that bores deep into the steel rather than thinning it evenly. While active flow typically suppresses this biome by sweeping microbes and water away, a dormant or stagnant line allows these colonies to eat through the pipe wall from the inside, often remaining undetected until a sudden failure or rupture occurs. The condition of the pipelines during the shutdown is a core dispute. Sable Offshore's position is that the lines were evacuated, cleaned, and preserved with inert nitrogen shortly after shutdown. In theory, a nitrogen-filled pipeline excludes oxygen and moisture, which would halt internal corrosion. The regulatory and environmental counterpoint is that pipeline cleaning is never perfect. Residuals, sludge, scale, and water almost always remain, especially in low points and deadlegs that nitrogen purge cannot fully reach. Over an 11-year period, even small amounts of trapped moisture can sustain localized microbiologically influenced corrosion. Nitrogen preservation also does nothing to address external corrosion under insulation, which was the original failure mode. The next debate is about restart risk. Restarting the system is not a simple valve-open event. Introducing hot oil into a cold pipeline causes thermal expansion. If corrosion has thinned the pipe wall, that thermal stress can trigger a rupture. At the same time, thousands of seals, gaskets, and O-rings across the Las Flores Canyon facility and the offshore platforms have been dormant for more than a decade. Many of these components will have hardened or lost elasticity. As a result, minor to moderate leaks during initial repressurization are statistically likely. This is why regulators insist on hydrostatic and spike testing. These tests are designed to conclusively expose integrity weaknesses before oil is introduced. From Sable's perspective, that testing is dangerous. A spike test risks converting uncertainty into proof of structural failure, and a test-induced rupture could be fatal to the asset. After more than a decade of dormancy, the primary risk to the Las Flores pipeline system is not whether corrosion exists. It is whether those risks are understood, bounded, and provably mitigated. Since 2015, Sable has focused on eliminating the original failure mode, exposing and repairing degraded pipe, improving corrosion monitoring, and restoring integrity management systems that decay during inactivity. Counterintuitively, hydrostatic testing and controlled restart reduce risk after long shutdowns by forcing hidden weaknesses to reveal themselves under controlled conditions rather than during live oil flow. Dormancy increases uncertainty. Testing and restart convert uncertainty into measurable, regulated operating limits, which is why regulators insist on them and why a successfully tested pipeline is safer than one left idle indefinitely. This is Avi. Like and subscribe. On to the next.